Thanks, everybody. Is it all right if I take a picture of you all? I started doing this a few years ago. Oh, is that you, Pablo? And yeah, I know your name. I tried to learn a few of you, so don't make me call on you in class, all right? Good. Well, actually, I'll take one with you. All right. It's fun because one day you'll be older, like me. I can't believe it, but I'm going to be 50 next year, right? It happens to us. But it's fun to go back and look at pictures from seminars and things from like 20 years ago and like, that's why I know that person. Now they're, teaching at so-and-so, or they've got this company in that place. But thanks again for having me, and glad to be here, a little bit cooler. I'm here in the Sacramento area of UC Davis. I am Greg Barron Gafford. I'm a professor in the School of Geography, Development, and the Environment, also with Biosphere 2, which is a research facility north of Tucson, about an hour. Has anyone heard of Biosphere 2 before? Yeah? Well, it's this place that a billionaire, Texas billionaire, built, thinking about innovation. He built it in the 80s because, as a program, NASA was thinking about going to other planets. And he was a real estate guy. He still does, buy low and then sell high. So when Disney was struggling, bought a lot of Disney. When downtown Fort Worth, Texas, where he lived, was struggling, bought it up and made it better. And then did two things: made places a lot better, but then owned, a lot of that. And so he built Biosphere 2 as kind of a prototype for places you could live on Mars or the moon. But then ultimately Columbia University took over this 3.5-acre area that had a bunch of different ecosystems meant to support human life. And it was a climate change research ecosystem study space. So the instructions for this talk were to tell a little bit for the first 10 minutes about who you are and how you got where you are. So that's why I'm doing this. I don't know if that's normal. You're supposed to follow those rules. So this is me being born on Halloween. So I'm a Halloween baby. Born to a single mom. And I feel like that's important to acknowledge because that shaped a lot of my childhood. Me and a little brother who were definitely latchkey kids, got to do whatever you wanted after school, but it was a good way to build resilience really quickly when no one noticed if you were home for hours on end. And I was the first one who was really interested in school. I was the oldest grandkid to my grandparents. I really appreciate the reading of the land acknowledgement, working with some of the Indigenous Resilience Center folks at University of Arizona. There's a practice of saying not only who you are, but what your tribal affiliations are. Like, I am from this clan. And that's been really meaningful for me because my grandparents have both passed on now. And to acknowledge that I come from people of Mexican heritage, like before Texas was a state, which is, if you're from Texas, a really important thing to acknowledge that you're from Texas. And then from a Polish background, and they were both farmers and ranchers. And so that was my experience. Being outside, doing whatever you wanted, learning by curiosity, and then be interested in school. And I was the oldest of all the grandkids, and so it was a new thing each time, like being the oldest. They actually referred to me as their number one grandson, which I thought meant they loved me the most, until I learned later it's just because I was literally the first one. And in doing all of this, I'm tall, but they thought that I should be a basketball player, which is that was not going to happen. I'm not that tall. And so what was I going to do? Was I going to work on a farm too? Was I going to do construction like my dad? But I was really interested in school. And so my great uncle was the one who said, you should go to college. Like, you could do this. You could be the college kid. And so I did. I studied a lot of biology. I liked science. I was okay with math, but I really loved science. And so I thought, well, I'll be a doctor. That seems like a overachieving thing to do. But then I was also working all through high school And one time working, that's from Arrested Development, if you know that show. If you don't know that show, you should find that show. Working at a grocery store, cut my hand open, and that was me. I just completely fainted. And that's when I was like, okay, I cannot be a doctor. I cannot see blood. That's going to be problematic. And so I then took that passion for wanting to do something in the sciences, but living in and getting to explore really remarkable places like Western Texas. And that's when I discovered that there was a field of environmental science. Not only is it, or was it in the 90s, the last chapter in the biology textbook, but it was going to become a field. And so when I was looking at schools to attend, University of Texas said, we're going to create an environmental science program, just come here and trust us, and it'll be biology, but eventually it will be environmental science. And I ended up going to a different school in Texas. But I looked at this and I started to think about, there's so much going on here. Like, why are the plants the way that they are? Like, how do we have so many different types of plants? And how they've evolved to live in these places? And the animals that are in these places, how have they evolved to be here and survive these things? And so I did study environmental science growing up. But then it was time to graduate. And then what do? A lot of the environmental science programs at the time, especially in Texas, were not about studying and protecting this. It was about how do you extract oil from this and stay in compliance. And so we took a lot of classes. Our soils classes were about finding contaminants, not understanding the microbiology. Our geology classes were about exploration. And a lot of the environmental law and plant classes were about making sure you didn't violate those rules. And so then I wanted to study more of plants. Being the first generation college kid and now going to school for the second time, which my parents certainly didn't understand, went to Georgia to study loblolly pine exploration. I went into this as an ecologist. But again, loblolly pine is mostly grown for pulp and paper production. So it's this interface of like ecology and industry that I thought would be really interesting to explore. But this is their worst case scenario. They would much rather spray herbicide and get rid of those weeds to make the pine trees grow without competition. And so when this was time to go measure the tree diameters and everything in these plots, they were like, okay, hippie kid, like you go to that one, we're gonna go to the one that just looks like a national park. So that's when I really learned about like, how do I work with industry when I'm having these challenges of connecting what I thought were my values to how things are being done. And so I studied there, master's in forest ecology, learned a lot, raised lots of questions about what I wanted to do and how I could make a place. And that's when I ended up moving to, this is Biosphere 2 at night. And so it's this research facility, 3.5 acres under glass. People lived inside this white area for about 2 years, like solidly. Like there was 8 of them, so about half this room. Suddenly you're living together for 2 years, doing all of your farming and everything else, as if you're trying to then like the biosystems engineering. You needed to balance out all of the carbon dioxide you're putting out as a human and replacing that with oxygen. You needed a way to cycle the water. And that's what they were studying. But inside this area, they were studying poplar trees. Again, a pulp and paper, carbon scrubbing potential system. So then I got to do forest ecology, but live in a desert. And that's how I ended up here. A theme here is serendipity, right? Like none of these things actually make that much sense when you connect them, except that I had randomly met people on, seminars like this, attending seminars, so that then when there was a job posting at the Biosphere, but I lived in Arizona, but I lived in Georgia, I could say, I saw your talk that time. So I am an introvert, but I encourage you to occasionally try to be an extrovert and meet those random people. And so this is what I did a lot of my PhD on, and we're transitioning to the agrivoltaics talk because this is a mesquite and grassland savanna type system. So this is southern Arizona. a lot of Arizona looked a lot more like grasslands before the 1800s, when cowboys came through and you got paid per head of cattle you put back on the train. And so that meant they were bringing more cattle. We didn't have range science yet. And so they brought in a lot more cows that would overeat the grass, so they're really good lawnmowers. Then there's no grass left, they're tilling it up looking for grass. Then they're not eating the pokey things like the cactus and the trees, but they are eating those fruits. And so now they've mowed, tilled, and they're leaving behind fertilizer patties, and you get this transformation of the landscape. And so see if you get the analogy between studying this and studying agrivoltaics. I was looking at a land use change that was happening because of a human involvement, and it was altering how water and carbon and energy moved through a system. What kind of carrying capacity does that ecosystem have for supporting other uses, other sources of life? What is the diversity that is in this space? And diversity is really important, especially from an ecology perspective, because if you have less diversity, in this case in the number of grasses, it takes fewer things to wipe out your biology and all of that carbon and water cycling. Also, part of what I was studying was the relationship between the trees and the grasses. Ranchers saw the trees as a problem because they assumed that there was some competition for the light and the water. And so the practice still today is to try to take it back to the grassland. This is not what it should look like. It should look like what it looked like when I started here, or the historical pictures I've seen. I'm talking about land use change now too also. And so there were practices of just dragging chains between tractors to knock the trees over. They're setting the whole thing on fire, trying to knock back the trees and bring the grasses back. And a lot of these things, like, it wasn't happening. There still was this land use change happening outside of a lot of their interest. And so they also assumed that the trees were stealing all the water that the grasses need. They didn't really believe in agroforestry, which is a practice happening around the globe. And so a lot of our work was documenting just how well these plants were doing in the shade of the trees. Actually, the grasses that you want your cows to be able to eat are thriving in the shade of the tree because it's so hot and it's so dry here. And so what happens in the shade? Well, in the shade, your temperature goes down, right? I think we all know that. You hide in the shade on the hot days here in Davis. Another, if you spilled your liquid, coffee or water, which one's going to stay wet longer, in the shade or the sun? Class? Shade, thank you. And so these were these principles we were documenting, trying to get the farmers or the ranchers to do something a little bit different. And so around that same time, while I'm just happily doing dryland ecology, and we're also setting up new types of equipment to measure not just individual plant responses, and this is what I was talking about, Ben, these systems that allow you to study overall carbon and water fluxes in this system. You can literally monitor without touching how much carbon is being scrubbed out of the atmosphere using these techniques and the amount of water going back to the system. And around this time, someone from Pima County commissioners said we're getting all of these questions about heat islands coming off of renewable energy installations. Can you set up your equipment and measure that? And so this is what it looks like on the ground. Then we set up one right next to a solar facility. And we're like, well, yeah, I think we can just apply our ecology to this renewable energy question, which is another type of land use where you're changing the background vegetation, you're introducing a new surface, in this case, a black solar surface, but you're also introducing, some human dimensions and what they believe, whether or not it's founded in truth. And so you're battling not only the science, but perception. In this case, for this particular solar installation, the neighbors over here were so worried that there was heat radiating off this solar array that they put in a 10-foot cinder block wall. Which one of those do you think made a bigger heat source, the wall or the solar array? And they only blocked it on this side. That farmer didn't care. And so it offered us an opportunity to study both of those things. And so we were excited, like, hey, we can go out there and measure this. We can put some numbers to these questions. And for me, this is where this field of agrivoltaics started. we did find that the photovoltaic heat island effect was real. Large-scale solar arrays were creating hotter areas inside the local solar array than outside. But this was another learning experience for me as a young faculty person. Was the editors at Nature Scientific Reports only allowed us to have 4 figures. Figure number 5 was showing our measurements as we moved outside of that solar array and how it only reached about 30 meters. And so we just said that in the text. That's when we learned how we were going to be misinterpreted for the next 15 years as people who sometimes purposefully misinterpreted metric units would say, well, that Baron Gafford study, they said it's going to heat it up 42 degrees. Where he came up with this number, I will never know because the lawyer will not talk to us. We actually say it's about 1.5 degrees Celsius, so do your own math conversions. We say about 30 meters outside of that farthest solar panel. He interpreted that to the court as 1.5 miles. Also very incorrect. And so that's when we started to run up against that. And in here, like, why was that happening? And I understand that y'all are a mix of engineering, all kinds of different fields. So I'll walk through some things some of you may understand. Like, energy isn't created or destroyed, right? It's just changing forms. So all that sun energy is coming in, and it either soaks into the ground as a heat flux, it returns back to the atmosphere as the heat you can feel, which is sensible heat. The other thing it's doing is latent heat exchange. Have you all heard that term before? So like that, in that energy release and that conversion of water to water vapor. When you get rid of all the vegetation as they were doing, that energy leaving the system still has to be the same. Now you've got a new energy of this. This is the renewable energy capture from solar being solar. But without all that transpiration and evaporation happening, you just had more sensible heat flux. It was just warmer because of that, how the energy had to get out of there. And so if this was true, we could do the opposite. We could then reintroduce plants and balance out the system a little bit more. You could put in grasses, as Rebecca Hernandez talks about, where if you now are going to drop that red arrow back to closer to what it was before, and depending on the types of plants you re-vegetate with, you can even release more energy through these blue arrows. And the solar industry was caring about this because a cooler solar panel is a more efficient solar panel, as many of you know, which means even if you're only getting like 2 or 3% increased production, that's big when you're talking about larger scales. So this was around 2010, 2011, when I was rejected the first 7 times. We would pitch this to National Science Foundation, and every one of those rejections would say, well, don't you know plants need sunlight? I'm like, yes, I do. That's actually what I study, but never mind, I must not have said it correctly. You just have to take ownership of that failure. But then we were doing these native grasses, and this is where it becomes to have been working at a university with undergrads. You all remember being undergrads, right? You weren't always 100% responsible. So the undergrads helping us with this project, we literally had one solar panel that we put on sleds so we could slide it over the bare ground and the grass. They went to the Grand Canyon for the weekend and didn't tell us. What that meant was all of the grass not in the shade of the solar panel was dead by the time they got back on Tuesday. The grass underneath the solar panel was perfectly fine. And that's when I was really like, oh, duh. Like, of course, it's also better for the plants. And so then we started to work towards like, well, if your goal is to cool down solar panels, which was our goal at the time, don't go with native grasses that are really evolved to hold onto that water. Go with plants where you already lose a lot of water in that agricultural process. And so this pivot point is where I went from doing what is now called ecovoltaics to the agricultural voltaics. And that was it. It was as simple as that. That was the goal. That was my worldview at the time. You can tell how old it is. This is my picture I have to show. So yeah, we started to ask this series at the Biosphere, like, what if the rainforest, blah, blah, blah. But ours was, what if we could produce our food under solar panels? And so we made the first agrivoltaic installation in the US, at least at a university, which all we did was elevate the solar. It's on way too much steel because we were the first, and the biosphere gets about 100,000 visitors a year. And so that came from risk management as 100,000 opportunities to be sued when it fell over. And so they like super over-engineered it, and is not what we do anymore. So that's how I got here. I don't think I have to convince you too hard, so I won't spend too much time on it, but we have major challenges across our food, energy, and water sectors. A lot of times we talk about intersections of these different challenges, and I feel like y'all are probably pretty aware, but I like to stress that this is not just a Arizona or California problem or even a Southwest problem. The United Nations has a series of sustainable development goals, recognizing that whether you're a developing or a developed country, we have limited resources to try to right some of our trajectories in terms of climate and the pressures it means for our well-being. And so how are we going to start to solve these solutions? And some of this food and water intersection is showing up globally. I show this picture because of some challenges we're working with our French collaborators, but I'm sure you similarly see it here in terms of luxury things like wine production or table grape production. But it's also showing up in Arizona in terms of empty canals. And I'm not sure if y'all are at this point yet, but this is someone who I'd now call a friend-ish as opposed to complete strangers, Nancy Kaywood. I first met her because the farm next to her was being sold to a solar developer. And she was really nervous about it because she had heard about these 42-degree warmer temperatures reaching 1.5 miles, which would certainly wipe out all of her farm production. And so she was rightfully freaked out. The lawyer was saying it in the Casa Grande newspaper. And so now, when I get this question, even as far away as Spotsylvania, Virginia, they're like, we've got 2 sources of evidence here. And I'm like, well, that guy's a lawyer who misinterpreted our paper, but I see what you mean. And so farmers all over central and southern Arizona have lower water rights, which means that they are among some of the first to lose access to water. And so some of these farmers 2 years ago were getting a 25% cut to the allotment of water they got for growing food. So now they may have had 100 acres, but they've only got water to support 75. Then last year, lost another 25%. So now they're operating with half as much water to grow food. And you're starting to see this show up to where you see this whole scale transition of large swaths of area no longer having the water to grow food, and so they're switching to producing renewable energy. So where's the answer? We need renewable energy to make our energy transitions and meet our state, national, and global goals. But a lot of times across our state and many places in the Southwest, this is what it looks like on the ground. So I feel like, unfortunately, we've been kind of siloed in terms of how we've been trying to move towards solving these different challenges. We're out of water, let's put in solar. But I feel like we could do more. And so we're trying to move beyond these siloed solutions and talk about, if you've got these goals of maintaining food production and more food resiliency in your own community, but with less water, so you need to maintain access and maintain pools of water for future generations, how do you move towards some of these clean energy solutions? And so this is an aerial image of one of the sites we're starting to work on now. And honestly, it looks like it could be on the moon or Mars. It's so bleak because the practice has been, for the ease of maintenance, to get rid of not only the top vegetation, but even the seed banks, so the top few inches of soil. And it's really hard when we see this as the alternative. So this is our site in our agrivoltaic site, this agriculture plus photovoltaic site in Colorado. This is a site getting at that intersection of energy and human needs and farm sustainability versus lawn policy. With Jack's Solar Garden, the current generation of owner right now, Byron, was growing alfalfa there just like his grandfather had, but he was not getting the rain that he needed anymore. So he needed to rely on irrigation water. The way you do it there is you petition to get irrigation water through their canals, but he wasn't getting it. And so he started to petition to multiple watersheds to get water to that canal. And there simply wasn't enough to go around. And so he was losing money year after year. And as an individual, he's losing money year after year, but he's also trying to farm. So you're using some water resources to do that period. You're out there with a tractor, and so you're actually emitting carbon trying to make this work. And finally he said, that's it, like I'm done. I'll still use this land for good and I'll put it into solar. But the zoning board said, no, you're agriculture and that's industry. So you can't do that here. And it was around that time that we were able to connect and say, what if you do agriculture plus? And in this case, agriculture plus solar. And so we're trying to, again, move beyond those individual solutions and try to think more holistically about all the sustainable development goals. One of our goals is to start to partner more and more around achieving some of these goals, and that's part of what Ben and I were talking about this morning. Within the US, create partnerships that are taking a holistic look at some of these benefits. And so that's what we have been doing. And so we and many others at this point have shown that agrivoltaics can positively impact the food system because of that introduction of that shade of different degrees. We can impact energy because we can cool down solar panels depending on what we're growing underneath by about anywhere from 4 to 10 degrees Celsius. Like that's impactful. And in terms of water, because of the farmers in our area getting those massive water cutbacks, we started introducing that as another treatment in our research. Is instead of providing like initially just like a glorified science fair project where these plants in the full sun get this amount of water, these others under the solar panels get that same amount of water. We're growing mushrooms. So like we knew we had not on purpose. We ended up having wild mushrooms show up. So we knew we had too much water there. And so then we just cut both of them also by half. And so now we had a full and half irrigation. So half irrigation in the full sun, like they're gonna die for science. But the half irrigation in this agrivoltaic system let us see what could farmers currently experiencing 50% water cutbacks still be able to do because of the renewable energy. So we turned it instead of a land use conflict of food versus energy to continued food because of the energy. So now we're at this stage where we're wondering, like, what does it mean to scale agrivoltaics? This is a question we get all the time. And at first I gave into the pressure, and you're right, said, you're right, we should take our stuff that we've been doing on this like 1/8 of an acre and like start to look at thousands of acres. But more and more I'm starting to question, is that always what it means to scale? In some ways, scaling agrivoltaics means taking those same kind of community scale installations and trialing them in different places. Because another thing that the instructions for this talk asked about was thinking about justice and what it meant for people. And at each one of these agrivoltaic installations that we have around the world, each one of them is associated with a community. And so I'll dive into an example from Kenya in a minute. But I know that the impacts of this smaller installation are more expensive. I'm not going to argue with economies of scale, but the level of impact that is staying local is definitely more great. And so it turns into a question is, are you trying to solve local problems with local food access, local return of that investment, or are you trying to go large, which is what it takes to meet some of our renewable energy goals at like the county, state, national scale? This is an active area of research for sure. So our project in Kenya that I'll talk more about is much more on the smaller scale. While we've been building this project out, Kenya's largest solar installation, just solar, not even agrivoltaics, came in. And all we heard about was how terrible it was. Mainly because we were not hearing from the people that were getting that direct benefit. That energy is going to the city center, where 75% of people are not in city centers, still don't have access to electricity. So they were seeing all of this land provides something that was leaving their community. They saw the impacts on migration of all the wild animals. People go to Africa usually to tour and see. And the pastoralists were now having to alter their own livelihoods. And so I think it's a really great question to struggle with. Sometimes we're stuck at larger scale installations because that is where the industry is. But there are also opportunities, I think, for y'all, being the next generation of developers and doers, to think about ways that other scales might operate. So I modified this a little bit because Ben and I were talking about collaborations and connections. And so we've been working at this smaller scale, creating an agrivoltaics living lab, like really a global collaboratory, where this is what our initial installation in Arizona looked like, this elevated structure. And we started to then just replicate this in other places to capture what are those energy production benefits. What does it do in terms of helping the plants perform underneath? What are your water savings capacities? What is the carbon scrubbing potential of land when you introduce agrivoltaics versus just agriculture? And by partnering with folks around the globe, we've been able to not only update and better our design through times, but also lean on the fact that other people are better at some things than you are. So the folks in Mexico are much better at that renewable energy design. And they also were asking very practical questions like, if you now basically have a solar roof of sorts, why aren't you collecting the water? And then also using that to be more self-sufficient. And so they added that to their system. Our team in Morocco, who is more interested in working with saline soils and brackish plants, is adding that dimension to it. This is our site in, I'm not sure what's happening, there we go. Our site in southern Israel, which is focused on hyper-arid conditions. The site in Kenya, we also have one in Tanzania that is looking at all that comes from community integration and what it means to work with schools. And that's the project I'll talk about next. Somewhat to convince you as people who might end up in larger scale solar industry that there are reasons to work at smaller scales. And I feel like there's going to be a whole blow up of new startups that get into this space. So what we've been doing remember, if you track all this back, I'm just a kid from Texas who liked science but couldn't be a doctor. But now suddenly I'm getting to go meet communities in other parts of the world and learn about not only their cultural ways of being, like where are all the guys? Why am I the only man here? Well, most of them are the pastoralists, or they have left and gone 5 hours into Nairobi to earn more money, if that's possible, which meant a lot of the moms and grandmoms were the ones in charge of the kids. And so they were talking to us about their nutritional needs, what they used to grow. I'm going to back up real quick also and say, among all of these different places, we represent an aridity and a temperature kind of climate gradient. So Israel and Morocco, they represent Arizona's future in like 25, 30 years. Hopefully for Davis, it's more like 50 plus. But we represent the climate future of East Africa in terms of aridity and temperature. And that's part of why we set this up. But then in the times we were working there, they were going through 3 years of drought. Like they didn't have either their winter or their summer rains. And so they suddenly weren't growing anything. And this is what a lot of the ground looked like. Very bare. Even the smallest weeds were being eaten by the goats that were being brought through. And so we were then talking with the teachers about, is there a way that we can make this an educational program? They're like, I guess, like mostly we just need food. And so if that works, that would be great. And then talking with some of the farmers about like, what are the pest problems that you have here? How often do you water? So learning from the community about what their practices were, making sure that we knew all of our design constraints if we're trying to develop a new kind of system or approach. And a lot of them were getting water, by 5-gallon buckets twice a day and during the really hot times. And so the teachers were actually telling us about attendance drops during those dry times because the kids were also needed to carry water. And so it's very much a community program to try to get any kind of crop growing here. And so we wanted to know how some of these different crops that they had told us were their staples would do in an agrivoltaic setting versus a full sun setting if they did nothing. And so we wanted to be kind of like grow some of their plants in our place and see their climate future. And so we did that with Kenyan kale, a big leafy kale. Cowpeas, anyone heard of cowpeas? Yeah, it's a legume, kind of like a black-eyed pea. Think about that. Very common and very popular in a lot of dryland communities, including our own indigenous communities here in the West. Zucchini, another thing, just like we would be eating. And then Kenyan spinach, which is what we would call Swiss chard. And so we grew all of those. We imported those seeds. In case anyone's listening, we did it legally. And then grew them in our own agrivoltaic setting and our own full sun setting. And here's a few graphs. I wasn't sure how many graphs to show because I wasn't sure what the audience was, but we got a few here. And so what we're looking at is yields in grams per plant, so we could scale this up for a few of those varieties. Spinach, cowpeas, and zucchini. The agrivoltaics bars are in green because plants tended to stay that way versus the brown, which is how a lot of the full sun things ended up. But look at this, spinach is 3,000 times greater in this agrivoltaic system. I mean, 3,000 times. Just think about like how many more people are receiving food because of that yield that happened in that setting. And that's such a crazy large number that it makes like a 200% increase in cowpeas and zucchini almost seem like it's not so great. But if we didn't even have that bar, we would be talking about like massive increases in yield. And so this is what I mean when I'm talking about your renewable energy efforts can mean sustained agriculture in some of our dryland places. We also did that work of cutting back irrigation. So in this case, they are struggling to get water in that place. And so we said, well, what if you could only get half as much water? What would the impacts of agrivoltaics be? And so spinach, you still saw a yield increase. Cowpeas even did better with less water. Think about that one for a second. And zucchini didn't really care. Like, you cut back half the water, fine. What that tells me is that we could cut it back even farther. And so I'm not an engineer, but thankfully I work at universities with some. And so we've been working with an engineering group to design a precision irrigation system such that we're only delivering water when it dries below a certain threshold. And so some of these plants are obviously leaving more water in the soil or drawing more water out of the soil. But in all cases, under agrivoltaics, the drought-like conditions still meant that food production was possible, whereas some of these crops were just going away. So again, we're trying to change that narrative from food production because of renewable energy. So now at this point, the project in Kenya has been greenlit. We've raised the funds. They're about 5 hours southeast of Nairobi. And what this project represents is good intentions not panning out originally. So the river is up there like where it says Living Lab in Kibwezi, this town nearby, where they were pumping water using diesel-based pumps to fill this reservoir. And then that reservoir being higher could then be used for gravity-fed irrigation for the families of the community around it. And diesel pumping was great until the costs became too high, and then they stopped using the diesel-based system, which meant this is what all the fields looked like. Not great. That's where those challenges came back. And so this is where we stepped in and said, if you're going to be doing solar-based pumping, let's figure out what that percent increase cost was to elevate that and then bring all these other co-benefits. And so then again, there we are working with the moms because that's who is maintaining a lot of the local households. They're the ones who are actually going to be bringing food back into space. And you can see the elevated structure. We were trying to do, it's a science project, right, still, so we've got our rulers, we're measuring down, 4 centimeters, planting each one. There's definitely still some language barriers because most of them do not speak English. We got the idea that we were moving too slow when we were like, the trays were taken from us and they were just like, just punching holes and dropping plants in. So it's a measure of doing science in a community-based place. And since March, we've now had 3 cycles of food coming out of this system and then going to the school. And I include cabbage here because it stands out. Cabbage is one of those crops that the moms were mentioning that was not growing there anymore. They used to be able to have it, their parents had it, but now it was just too hot, it took too much water. And by growing in this agrivoltaic setting, which admittedly has a lot of space overhead too, we're able to grow these crops that were no longer possible there, and then it's going right into that community. So in addition to being able to provide educational opportunities, it's just an impact of food. So the other end of scaling is to just go big. And that's another project that we've just gotten funded from the US Department of Energy. And so to give me a chance to drink, I'll ask you a question. What do you notice about this aerial image of where our site is? So far, I only remember Pablo's name from this morning. Pablo.
There are a lot of gaps, like some green spots, but a lot of gaps.
Yeah, there's a lot of green, there's a lot of dark, but there's a lot of gaps. That is the former agriculture of this area still leaving an imprint. You can see in some of these gaps, if the image was better and you're actually at a computer, you can still see the old row lines in there. So there's a lot of non-agricultural land that used to be agricultural land. Remember that people believe that this is still an agricultural land, even if what we're seeing is that they've lost a lot of it. It does not mean they've changed their identity or their perceptions or what they think is supposed to be happening here, but great observation. Anything else? Yeah.
It's quite dry.
Yes, it is quite dry. We are one of the wettest deserts in North America, but we still get on average about 12 inches of rain. About 6 of it is in the summer. And so how is all this agriculture happening? Well, you can see when you're not putting water on it, it is quite dry. And so we are able to do, or were able to do agriculture because of other water inputs. And so recognizing that's your reality. And if you have less access to water, you're going to be challenged in how you approach agriculture here. Another thing, especially if this image was a little bit darker, like it is on a screen versus the projector screen, is there's a lot of solar coming into this space. And so that means that a lot of the people who live here are seeing their friends leave, like the other farmers. They're seeing less ag as they drive back home, and they're seeing that damn solar everywhere. And so some of them are getting quite annoyed by how much solar is moving in. And so what it's meaning is that some of the solar industry in this area, even at the larger scale, are asking how can we do something even a little bit different, even like leaving the soil behind, even like maybe revegetating with native species. For one, so that they don't get blocked in permitting, their projects actually get through the entire phase, but two, so they can feel better about what they're doing. So if we zoom in a little bit, this kind of like nauseating image, if you move your head, is what our solar site looked like. Again, like there's no vegetation really there to speak of. The practice prior was to pay about over $100 an acre for a couple of guys to come through and eliminate the weeds with Roundup. And that was not something they were excited about talking about. And so we designed a project where we're trying to look at these larger scale trials of a bunch of different crop types. Because people ask us all the time, like, how does that work? Can I do it where I'm at? Or what's the best crop to grow? Which is another really hard one because, wait, what do you say? And so we at least are choosing really large different plant types. So we can say, well, we're going to do potatoes, a leafy green, a melon, and a perennial. Because we only have so much space, we also only have so much staff. We're talking about full acres of these things. But then we try different products. And we've also set it up where each one of these connector boxes or junction boxes are what we're growing in that one spot. So before we had planned on growing rows this way, but once we found that this clump was one we could get data on the energy production, we started to clump our treatments that way so that everything about potatoes will then tell us about energy production in this block versus this block that had the leafy green of kales. We're also trialing some things that are more climate smart or more indigenous to that community or this region. Things that require less water input, like native beans and artichokes, chiltepine pepper, which is a very high value pepper in our region. But then also things that would require even less people milling around in a site if you had to start to try to work through issues with site access agreement. So agaves, where you hopefully are doing very little work and even getting in there very, very infrequently, or prickly pear, which are being harvested both for the fruits and the pads. And so we're offering a gradient of water needs and a gradient of the amount of time someone would need to be inside there. So why might this actually work? How are we doing on time? Okay? Yeah. Why might this actually work? Well, you all know that PV arrays are designed to maximize the level of light capture for solar production. What that means for me as a plant person or a person trying to design a system with that constraint of the industry has it at this density of row spacing and we can't change that if we're going to try to do this at larger scales, is the top of this panel should not shade the bottom of this one. Okay, so now I understand that at some point a lot of this area is going to be in the shade and that amount of shade is going to change through time. But as you said, it's really dry there. So the other thing is thinking about when it actually does rain, the area in that middle space is not only getting the amount of incoming precipitation that naturally falls there, is that it's also going to get all the water that would have landed on that solar panel and then spilled into that in-between space. Right now, when there is no vegetation there, this is one of the things that they have to get special permitting around to not create lots of erosion. So you end up with pools of water that are now concentrated, so maybe a quarter-inch rain or an eighth-inch rain, which is something in Arizona we still go outside to celebrate. An eighth-inch rain event can now turn into the equivalent of an inch-and-a-half irrigation event for the crops in that space. And because it's going to be in the shade longer, these areas are going to stay wet longer. And so we're putting all of these kind of like, oh duh, principles to work for us. And we're turning that liability of runoff into a resource. So that's why we're doing these different specialty crops to see what agriculture could mean right now, these more climate smart crops, and these native grasses. And I've just got two more things I want to get through. Is one, I think most of you probably realize that hotter conditions are resulting in some instability and unsustainability in our food system. And whereas before I've been talking about the plants, now we're pivoting to talk about the people. These background elevations in heat temperature, high temperatures that we're seeing, this continued high temperature into late September and in our case still in October. We set a record both in Tucson and Phoenix for the hottest ever in October. We set it on the last day of September for the hottest day ever in September. It was last Saturday, it was 117 in Phoenix. Can you imagine? Like, why does someone live there? They must not have many choices. But these high temperatures and then these heat waves on top mean really dangerous working conditions for all of the people that we rely upon in our food system. And the farmers are 20 times more likely to die in these hot regions, which are mostly in California, Texas, and Arizona. And the Biden administration is trying to do something about that by getting heat protection for farm workers into OSHA-type requirements. So now you're having climate change impact policy, impact laws. Texas actually voted this down. They don't want to have that kind of protection there. But what does it mean? Sorry. There we go. The slides got out of order. So what we've done is looked at, this is a map, so there's California, and here I am next door. And what we're looking at here is as you get into these hotter colors, this is work from one of our grad students, Tolly McTiernan. These are the amount of minutes until your body's going to be in a stress condition. And basically, it's not good to be black or red on these maps. So this is the next 20 years. This is 2040 to 2060 and 40 years off into the future. And you can see that in a lot of our food producing areas, the people doing that work are going to be under high pressure especially as we get out into the future. And so what we've taken is some information about patterns of shade in both our elevated and in our traditional ground-mounted systems in terms of air temperature and other factors that go into what the National Institute of Health calls human thermal comfort. The other way of getting at this is to take the infrared thermometer that you would usually use, like checking if you're okay at COVID, and checking your skin temperature while working in the shade versus the sun, and seeing that it's about 18 degrees warmer in the sun. And then we did some projections, and this is based on those different agrivoltaic scenarios, what that sun exposure will mean in terms of someone's ability to continue to work because they're not otherwise stressed. And you can see, well, obviously you dropped a lot of those really hot colors. And I'd like to note that, like, with agrivoltaics and even that intermittent shade that comes from tracking panels and farm workers out there pushes off what we're going to be seeing in the next 20 years to a solid 40 to 50 years out. And even in our Colorado site, which really hurts when they complain about being hot when it's 80 degrees, sometimes we've gone through and they're actually in the shade but working with their arms in the sun. People feel it. They're adapting in certain ways. So I'll end with, now how can we engage that next generation? And I mention this stuff because I'm pretty proud of it, and it's not the kind of things that usually go into your faculty portfolio. So one thing we're doing is working on really small scales, like with just a couple of solar panels and studying the impacts of agrivoltaics with kids. So in this setting, students are first learning about electricity and what it means to wire in series and in parallel, which is pretty fun. Learning about what it means to be shocked by 12 volts and how you definitely don't want that at higher. But then each class is given one of these setups. These are actually crates that are used for taking, the bolts and other materials to solar sites, and then they were getting collapsed down and then thrown in the dumpster. And then one of the guys from Enel Green Power said, "Oh, do you want these? You can make them into planter boxes." And we're like, "Well, definitely." And so we're reusing some materials. And even with this is taken in the morning so you can see the sun coming through, but providing some midday protection to these plants. This potential of agrivoltaics is detected at this 1 or 2 panel scale in a way that even kids can measure it. And so that's part of the work that we're doing. Another one is for those who we haven't been able to reach with these installations, is we've developed a game. And for those of you who like to play games, don't do it now, but you can download it. We have this new game which is called My Agrivoltaic Farm. It's now available on both Apple and, what do you call the other one? Android. Well, yeah, but what is that? Google Play, thank you. It's now available on both platforms. And this was developed through a USDA grant that we're collaborating with both Illinois and Colorado State on. And it's not only were the developers, but my own kids at the time were doing a lot of Minecrafting. And so there's a lot of Minecraft look in here. But you basically have to go through things that you would have to develop solar on your land. So, your regular old house, especially look how broken it looks. Your regular old house needs some work and needs some financing before you can even do solar. In this scenario right now, it's largely driven by agriculture. Eventually, you can start to grow plants and you get enough money to amp up your house to where you have that connectivity. Then you can add solar. And then what's really cool about this, and I've never worked with a game developer before, but talk about cool impacts, is then they were like, well, which crops grow really well in which places? Which ones are terrible? What does it do in terms of how much you water? Because you have to water, and you have to actually buy water, which is something else farmers would have to do. And now it's been replicated both for Arizona, but also Colorado and Illinois with the data that's come in. And so we can say, like the lettuces, they do really well. The beets did terrible. And so kids then get to learn, like there's plant-to-plant variation, and they have to learn about which ones do well and don't. Celery did remarkable in the Colorado site, so that's in there. Like, I hate celery. Why did that have to be the one? But it did like 300 times better, and that's built into there. And so we're working with some of the teachers on how to develop some, experiential learning in the classroom through this. And so there's a QR code, or you can just look it up on either of those platforms in My Agrivoltaics Farm. And the last little bit was also for Ben, who's going to watch it later. But we're trying to also then work with all these international partners to create a global school of agrivoltaics. And as we were talking about, we're still trying to identify what that really looks like. Because in Kenya and a lot of the more developing countries where solar is just now leapfrogging the way we did energy production and is becoming the predominant way, we not only need people who understand how to install energy, install solar panels, or just understand agriculture, but if this is going to be a new system that is out there more commonly on the landscape, we want to kind of elevate everybody's differential knowledge so that industries can then communicate, and that each new installation you have almost like an extension model where the previous learners are now not only finding jobs but becoming the teachers for those next installations. But at the same time, there's a lot to be done at the academic and the university settings. And so we met a few weeks ago in Mexico with people across all of these different countries at our site in Mexico. And so that is one other venture that we're looking to build out. So with that, I want to say a couple of things. One is we're looking for support in terms of students. So we're currently looking to recruit both master's and PhD students and a postdoc, not only in agrivoltaics, but in these other forms of climate smart agriculture. And that's our website, thesolarfarm.org. And so thanks again. Hey.
I'm curious, like, what kind of any testing you do on the soils to see if there's any like toxicity or like chemicals leaching from the solar panels and the soil.
Great. Yeah, so the question was, do we do any kind of tests on the soils to look for leaching or anything like that? Absolutely. Largely that was driven, again, like so many of our questions, from community concerns. So when some of the farmers were saying, even before they saw that we were growing our own food there, was concerns and then finger pointing of those solar sites are polluting the soils, which is polluting the water, which is getting into my land, and that's why my crops are dying. Not the fact that we're in a drought, but that. And so then we started to collect more of those soil samplings. The other question was, is there anything in terms of carbon? Are we losing more carbon out of this system because we've just accelerated the carbon cycle? It's nice and moist, soil microbes like that. Roots might be respiring a bunch, or are we storing more carbon? And so we've been collecting soil samples for both of those purposes, because we are telling people that here's new food sources, here's access. And then I think, I actually zoomed through it because of the slide issues. But we are having a farm to table event somewhere in here. Yeah, there we go. On November 8th at Biosphere 2, if any of you happen to find yourself in Arizona at the time. And so we are sending this food out. We're talking about nutritional access. And so far we have not found anything that suggests like, cadmium from panels is coming out of the way they're meant to be capsulated and ending up in our soils. But it's a great question. Yeah.
So what is I'm not sure exactly how to put this, what is the packing density of these agrivoltaic arrangements versus dedicated solar farms?
Packing density in terms of number of panels? Or
if you were to take, say, like square meters or square feet of solar panel per acre of land used, what is that compared between these agrivoltaics and dedicated farms?
Great question. So I'm going to zoom back to this.
A lot of your old, a lot of like the prototype arrangements were really tall and like really sparsely populated by panels.
Right. So I think that, again, comes back to the scale. And what we try to tell both farmers and the solar folks is just tell us those design constraints and we can work within them. So for this site, for the Colorado installation, there's no change in the panel density. That is as dense as the panels could be for his latitude, he's higher up than us, so which meant there was more space between those rows because they're avoiding the self-shading. And then we saw within that how much spacing can we put in terms of food production rows. And we debated, should it be 2 or 3? Because what you're actually doing is taking about 20% of the agricultural row spacing out of the equation by putting solar in that space. And so in this case, none. In the case of our different projects with the international sites, I'll just pull them up really quickly. You can see that the density of solar overhead is varying. That is really driven by those particular climates and just how much abundant sunlight there is and the crops that they wanted to grow. So really, I would have spaced this more out in the Mexico site, but they're really interested in the technology and the solar technology, and they only had so much of a footprint, and so they wanted to trial a bunch of different solar types, and so they needed every space. The solar density for this Kenyan project, I should have mentioned, is the amount of water that they were going to get to that reservoir determined the amount of solar that they needed. And obviously they have a lot of space there for solar. And so we knew that we needed to install 37 solar panels or 87 solar panels. And then we did the light modeling to say, based on the crops we'd want to grow, this is how much light you would need to let through throughout the day, and then space them out accordingly.
Okay, so the driving design constraint is the intended crop.
It's the intended crop, unless someone tells you I'm not changing the design constraints, deal with it. And then you might have to change the crops that you could do there. Absolutely. Yeah, great way. Yeah.
Yeah. So how does the energy production of the solar panels, how does it get affected by agrivoltaics?
Mm-hmm.
Is it a trade-off? Like you produce less energy from the solar panels when you have plants underneath them? Because I remember we visited a solar site, and they told us one of the guys told us that some of the sunlight gets reflected through the floor or the dirt or the ground back to the solar panels from the other side of it. So how does that?
Right. So I bet what that person was talking about was a bifacial panel where it's collecting on both sides. Most of the developing world is not using bifacial panels, and so that is already not a constraint. And even within many of the solar developers that we're working with in Arizona are not using bifacial panels either. There was a little bit of a bump up during the pandemic because of tariff laws that allowed for bifacial panels to be used at very similar types of costs, but we're not seeing that anymore. So if you ignore the bifacial component, the efficiency of a solar panel goes down linearly with temperature. And so what we're doing is using the natural process of transpiration to cool off that solar panel, which means you're moving up the curve. So it's actually more efficient. And based on some National Renewable Energy Lab modeling, based on how much we are cooling the panels, based on our micro thermometers on the back, it would increase at about 3%. Yeah, yes? Sorry, did you have a question?
Oh, you answered it.
Okay. Pablo again.
Yeah, where are the economies of agrivoltaics? Is like what economists call like a free lunch, or do you have like trade-off and, for example, a bigger or higher investment cost? Or?
Yeah, great question. So the question was, are there trade-offs in terms of initial investment costs? I think this is one of the most important questions, and it is a very big, like, cross-disciplinary thing to approach. Because depending on your design constraints, in this particular site I showed in Colorado, there was no change in the density of the panels at all. But what we did was ask that guy Byron if he would elevate the panels. And so he said, how much? And we said, we don't know, because we hadn't done it yet at scale. And he's taller than me, and he said, how about 8 feet? Because then we don't run into it all the time. And that's a lot of wins for that. But also that seemed like a lot. And so how about 6 feet? And it really was as rough as that. And so then to figure out what is that extra steel in terms of pounded down and elevated up. Now you're taking a very hard number like that and then calculating against your returns on investment from the agricultural produced. That seems like an easy economic question, and food, for the most part, is not very valuable. Like if you can go buy 8 ears of corn for $1, like why are we growing corn? Well, there's a lot of other reasons, right? So then it's turned into, for some of the developers, a question of all of the amount of energy they put into getting a project passed that might fail because someone says, well, that's kicking out agriculture. And so what we're trying to do is calculate both the soft costs, but also the soft returns that come with shortening your return on investment. I heard that's from Ben that some of y'all study life cycle analysis. Another question that NREL is really interested in is, does agrivoltaics extend the lifetime of the solar panel, which is usually going through these daily extremes in temperature, which is part of the wear and tear. But if we're reducing those extreme temperatures these panels are experiencing on a daily basis, does that actually prolong their lifetime? Is there a reduction in the degradation? So far, I mean, that's a natural experiment, well, I'll tell you in 20 years, but otherwise, that's the kind of thing that could be done with some of the degradation studies, and I haven't seen anybody doing that kind of work yet. Yeah?
So all of these examples are in pretty arid or very arid environments where I guess the fixed PV is,
Mhm.
I guess, maybe more, I guess the sun is more intense, the fixed PV is maybe more profitable. But is this feasible if you have like those rotating ones that rotate throughout the day?
Mhm.
Those are going to shade more plants, right?
Yeah, good question. So actually, I didn't show the video for sake of time. Which findings from the fixed tilt agrivoltaics, I couldn't finish it all. But actually, this site in Colorado is tracking. The new site in Arizona that we're building is tracking. So when I was talking about the water running off, it could happen either in the morning or the afternoon, so it would be spilling into different alleyways. But all of that is tracking. And so for some plants, especially plants that could use more shade, yeah, you are giving up some of the benefits of that shade protection in agrivoltaics. So then it's a good question of, well, when is it good to be in the shade if you're a plant? I'll tell you, the short answer is it varies by plant, which that's the science answer, right? It varies, and we need more money to study it again. But what we have done is gone through and monitored the plants a lot. Kind of like you can take your pulse throughout a day and see like when you're stressed out, or your doctor can. We can measure the photosynthetic rates of these plants throughout the day, and we can see that quite a few plants, especially in dryland environments, go through what is technically called, I didn't make up this word, midday depression. So it's like me without coffee, but plants, the sun comes on and they do lots of photosynthesis, but it becomes slightly too hot or slightly too dry in the air, even if you've watered them, and they close their little pores to not lose water, which means photosynthesis is tanking. And quite a few of these plants, even when you're giving them water, are turning off by noon. So like your worst employees, like they're done by lunchtime. And so the way agriculture is maintained in dryland environments is hit it with irrigation again so that it can open its pores, so it can do photosynthesis. So that means you would really want to protect the plants in the shady, you'd really want to give them shady conditions in that hottest part of the day. So if you think about the tracking panels, they're going to again be kicking shade onto those plants around 3:30, 4 in the afternoon. And so you will have given them morning shade, which is not great, full sun during the day, and then shade protection at the end of the day. And now that is your new reality, then that's your new design constraint. How do you plant within that system is the new question. Yeah.
I was wondering, for farmers who are interested in getting a setup like this, like, where is there information for them to try to figure out like what plants can they grow, how can they do this? Like, are there any consulting companies that already exist for people for that?
Yeah, great question. For those online or couldn't hear, she was asking, like, are there resources for farmers who want to do this, or solar developers who want to consider these types of things? And right now, there's a good resource, but it may be ending at the end of the year. If you go to the Agri-Solar Clearinghouse, they were funded by the Department of Energy for about 4 years to contain and gather all of that information. They weren't keeping the data, but they're keeping the stories. And what they were also doing was connecting it, and there's like, I think if you go to it now, there should still be like a little live chat boss that is staffed by a person in Montana, because that's where they're based. And they will say, well, like, hey, where are you at? And you're like, well, I'm in Sacramento. And they would say, oh, of all the people we've talked to who do call back, these are the 2 you should reach out to. Or you should check out these stories in our story bank. And so they were actually kicking off the doors, just like we did for our farm to table. They were like, let's bring the community in and see that solar is not scary. Solar is not radiating heat. Like, why would it do that? But it's not radiating heat that's going to harm you. And there are these potentials. And then they'll also help you point towards the REAP program, the Renewable Energy Access Program, to help farmers find some of those avenues. Great question. Hopefully it continues to be funded, but we'll see. Yeah.
You mentioned one of the cases of kind of like more probably like industrial scale solar farm in Kenya being on land that was formerly kind of for wildlife or pastoralism. So I'm curious kind of what the interaction is of kind of like selling agrivoltaics as a way to kind of make solar more appealing to people, but if that solar farm is being built in an area that never didn't have agriculture in the first place,
Mm-hmm.
kind of how those conversations are going, and yeah, if there's kind of an incidence of kind of the greenwashing in the agrivoltaic plays in the space where
Yeah.
you're kind of trying to sell an added benefit that isn't actually applicable to the land use.
Good question. So you brought up a few things there. Greenwashing because of agrivoltaics, which was a really big discussion at our international meeting, which was in Denver this year. And some on the renewable energy side were saying, well, isn't a little greenwashing okay? Like, this is an urgent climate crisis now. Maybe agrivoltaics is one more pathway for renewable energy to get into otherwise agricultural communities. So there's that camp. And there are a lot of people who are really worried about the greenwashing potential of this, especially if you're talking about lands that weren't formerly agriculture anyways. I think even at those large scales, it's going to be challenging to work through site access agreements and everything to allow a lot of people milling around in there. And so then it would be a question of like, what would be the best way to reinstill something in there? Unfortunately, a lot of what we were seeing in terms of the pastoralists were goats, which goats are not great in solar. Like sheep chew down and goats chew while looking up, which means they're eating while seeing everything you put there carrying electricity, in addition to be jumpers, right? Like, yoga goats. And so it's still an uphill battle. With this particular county, McQuinney County, the governor of the county was really interested in water savings. So he had done county planning, and what their goals were saving water. And so it worked here because they needed a way to reduce water use for agriculture. And it just so happened they were going to use solar. So it's not going to be right for everywhere, but thankfully, the amount of land area we need to meet our renewable energy targets doesn't require it being everywhere. It's about where it's best. Let's see, the green shirt?
So how do we go about washing the solar panels and the elevated steel structures like we saw in the pictures in
Mm-hmm.
Kenya and Israel? Because the efficiency would lose over time, right?
Yeah, well, not knowing who's online, I'll be cautious to say at one of our partner sites, the cable management has been another challenge, and this is related to your question in a minute, is a lot of the cables that they run between the lines were buried just below the solar surface. And then there was no vegetation there to manage the soil that was left. And now a lot of those cables are at least a foot above the ground. As opposed to a vegetated system, even sparsely vegetated, is going to be holding that soil down. And so from the early measurements we've made, we're finding less dust production or less soiling in a system what is with agriculture. And mainly because we're not doing a lot of tractor work and tilling through there anyways. And so we have not washed the panels at our original biosphere site ever. So like 9 years and never washed. Okay, he's been very patient.
Did you observe any kind of ecological change in any of the solar farms?
Yeah, any other ecological change? Do you have an idea more specifically what you're wondering about?
Mostly insects.
Ah, good. Perfect. Mostly insects. So the question was, are we seeing any other ecological change with respect to insects? So we do. Another question we get is like, does the changing of the light environment and the light composition affect, navigation of insects, or are there background sounds? These are things people ask. Is there so much background humming from the inverters that it scares off all the insects? Neither of those have been true. In fact, our group, who's been doing a lot of harvesting of the cowpeas the last few days, wishes that was true, because the wasps have been coming to do all of that pollination. And even though we turned off the water a week ago, which is how you get beans to finish maturing, and put buckets of water with sugar in them farther away to attract the wasps over there, they did not leave the agrivoltaics area. We still see a lot of bees. We see a lot of pollination. Some of the things we do see changes in terms of the plants are their phenology, or the seasonality of some of those plants. Plants go to flower when they're stressed out and they're done for the year. And because they're less stressed, we see a longer growing season. And so one of our questions have been, if at a changing climate, you're starting to see this, what we call a phenological mismatch between when the pollinators are there and when the flowers are there, well, agrivoltaics serve as one way to extend the flowering season so that those pollinators can find their little refuge. And I think that's another cool open area of study, but we have not been documenting any negative impacts either in terms of soil contamination, insect abundance, even though we're not entomologists and would love to meet one, or contaminants showing up in the leaves, or less nutritional capacity in the crops.